Swayam Prabha. Digital India. Educated India.
So, we were talking about the vibrations, free vibrations of a string, and we wrote the equation of motion of free vibration of a string using Hamilton's principle or the extremization of the action integral, and wrote Euler-Lagrange equations and got the equation. And we use separation of variables technique where w, x and t, that is a function of space variable x and time t. We wrote it as phi of x times q of t, and then proceeded in the process we defined the eigenvalue and eigenfunction. Okay. We said that eigenvalues are always, that lambda that we have here has to be non-negative. We also said that eigenfunctions are orthogonal, right. If you recall the previous part of the lecture, we said they are orthogonal. We also defined what that orthogonality means. If I take a pair of them, product of those when I integrate from 0 to L, it will be 0. That is the definition of functions being orthogonal as opposed to vectors being perpendicular to each other. Okay. Now, let us prove how this orthogonality comes. Our starting point again is this equation, and our trick is almost the same. The trick is what we did to prove that lambdas are always non-negative, and to define the concept of this Rayleigh quotient. Okay. What we did was we multiplied by phi and integrated. This is one trick that you should remember in this topic. When you have an equation, you multiply by something, the same thing, the whole equation, integrate from 0 to L and then see what happens. Okay. So, we will take that. So, we will start with, that is, we want to prove orthogonality. To prove orthogonality of phi I and phi j. Again remember, these are functions of x, phi I of x, phi j of x, that is what we want to prove. Our starting point, that equation that we have, t phi double prime plus lambda rho phi equal to 0. We will instantiate this equation for phi I and phi j, because we said there are infinite lambdas and infinite phis. So, we will write this as t phi I double prime, in which case I have to write lambda I rho phi I equal to 0, and other one t phi j double prime plus lambda j rho phi j equal to 0. Okay. Now, what we will do is this equation we will multiply by phi j everywhere, and this equation we will multiply by phi I. Okay. And then we will integrate from 0 to L. Okay. That integration I will do it here, so that will become cluttered. So, the same thing I will write 0 to L t phi I double prime phi j plus lambda I rho phi I phi j dx. Since right hand side is 0, even after integrating it will remain 0. Okay. Again we will do integration by parts for this. Okay. When I do that, I get t, first function I will take phi j, integral of second function I take phi I double prime, so that becomes prime 0 to L, minus derivative of first function, that will become phi j prime, integral of second function phi I prime, and then this is 0 to L lambda rho phi I phi j equal to 0. this is of course lambda I, and this thing is going to be 0 anyway, because phi I phi j, if you have, they have to satisfy the end conditions, that goes away. This is what I get with the first equation. Similarly, second equation, that is this one over there, the first equation when I integrate, that is this equation integrate, I have this thing. Okay. Now, the second one, if I do this, since I and j are reversal, I can just write it, right. So, I will write minus 0 to L t, wherever j is I will write I, phi I prime phi j prime, actually this did not matter because it is the same thing, plus 0 to L lambda j, I is there. So, I write j rho phi j phi I, and that did not matter, right. So, now if I subtract one from the other, right. So, what I get, this is plus minus. So, these two things are the same, they cancel, okay. And what I get here is lambda I minus lambda j into 0 to L rho phi I phi j dx, okay, I forgot dx here, right. So, there should be dx, this is equal to 0, right hand side is all 0, right. So, now we said that these two are two different eigenvalues. So, this is not equal to 0, then this must be equal to 0, that is the orthogonality. So, this is the orthogonality property, right. And then if you also say orthonormality, that is going back, we said we want to normalize it like that. So, the integral 0 to L rho phi I square equal to 1, that thing we say that is a normalization condition, put together we get orthonormality. Okay. Now, when we have this, the advantage of having functions that are perpendicular to each other is that any function, this w of x that I get, x and t, okay, that I can write as a summation of several of these functions. Okay. In fact, I do not have to first say time, let us just stick to space for now. W of x is phi I of x C I, that can be q I, function of time we can do, but let us stick to just C I right now, 1 to infinity. Okay. That is because if in vector calculus, if you have x, y, z orthogonal coordinate system, any vector can be expressed as a component of x, y and z, right. Similarly, here we have orthogonal functions by taking a linear combination, that is what we call it, linear combination. If you take, you can write any function. Okay, that is something that actually needs to be rigorously proved, but we can intuitively understand that when you have orthogonal functions, in this case we also made them orthonormal, you can get this, right. That means that any w of x that you have, or rather I can just call it, since I can just put like phi of x, any function, I can write it as I equal to 1 to infinity C I phi I of x. Who gives me all these C I's? What are those? How do I compute? Easy, the same trick in this business. What is that thing? We just multiply, take this phi and integrate it from 0 to L. That is, we take the function, okay, this phi is there, right, everything. I want to know C I. So, what I do is, let us say particular, let me call it C j or something, because C I is already there. Let me take it as j, phi j, I want to take C j. Okay. So, I do this and integrate it from 0 to L, because I know this phi of s somebody has given me, I want to know what are the C I's. So, I put 0 to L phi x phi j dx, I do the same thing on the right hand side, I equal to 1 to infinity. So, integral 0 to L Ci phi I phi j dx. Okay. Now, remember our orthogonality property. Whenever this I is going from 1 to infinity, whenever it becomes j, only then this integral that we have, I can also put rho if I like, but rho does not matter in this orthogonality relationship that we just did here. Okay. Rho is just a constant. So, whenever I is not equal to j, this integral is going to 0. So, only non-zero term that will be there will be Ci 0 to L phi I square dx or phi j square, here phi j, because I am taking j. Only when I equal to j, then it is not 0, and we had said that rho included is 1, or if I take this, okay, multiply by rho and then divide by rho. In other words, this is equal to 1. So, I get Cj equal to this, or what I get, Cj is integral 0 to L, it is this portion, and then rho 1 over rho goes there, rho phi of x times phi j dx. So, if I know the eigenfunction phi j, I can get the corresponding coefficient, that is Cj, that is going to be in this linear combination. Okay. So, there are a lot of nice things about eigenvalue problems, but let us come back to the Rayleigh quotient concept that we had discussed. This lambda has this particular ratio. Okay. So, this one has even more significance, because as we already said, even when the phi is approximate, lambda we come very close, but with an interesting property. So, let me write that Rayleigh quotient one more time. So, Rayleigh quotient for this problem. Okay. So, that in this case this lambda is integral 0 to L T phi prime square dx divided by 0 to L rho phi square dx. Whatever phi function that you take, okay, even let us say phi hat, not an eigenfunction, okay, let us say it is not an eigenfunction, that is, it is not the solution of our eigenvalue problem, which is T phi double prime plus lambda rho phi equal to 0. It is not a solution of that. Even then, when I get this lambda hat value, let us say 0 to L T, I have phi hat instead of that, phi hat prime square dx divided by 0 to L rho phi hat square dx. Okay. This will be greater than 0, this will be greater than 0, but what we find is that any phi that you take, this lambda is going to be less than or equal to lambda hat, no matter, this is any lambda hat, meaning any phi hat function you take, this will hold good. That is minimum characterization of the eigenvalue problems. Okay. So, when you have Rayleigh quotient, you take what you can guess some phi, you will get some lambda. That lambda you can consider is larger than the real lambda, fundamental frequency that will have, okay, that lambda you take. But then there are several lambdas, so we can propose a theorem that considers the fact that there are several lambdas. Okay. But if you are in the vicinity of a particular eigenvalue, no matter what function you take for phi, the one that you evaluate in using this Rayleigh quotient is going to be larger than the real value there. In other words, Rayleigh quotient is minimum in the vicinity of that eigenfunction. Okay. If you consider eigen if you say eigenfunction axis, whenever eigenfunction this phi the phi axis, whenever phi becomes an eigenfunction, corresponding lambda will be minimum, and that is the real lambda eigenvalue. Okay, that is the significance of Rayleigh quotient. Okay. Now, let us pose a theorem that takes care of this. So, what we will say is that lambda k is equal to minimum, Rayleigh quotient will come out of this, but we will just write it as a theorem, minimum with respect to some phi of x, again calculus of variations problem. That is why we are discussing this, because it is important in mechanics for this vibration problems, or which are also known as Sturm-Liouville problems. Okay. So, that is, well, let me write it because the spellings are, pronunciations are different, Sturm-Liouville problems. Okay. I think there is a U also, Liouville, Louis, some Louis problems, okay, or eigenvalue problems, that is easy to remember, eigenvalue problems. Okay. In all of those cases we can derive this orthogonality of eigenfunctions and all of that, and then this minimum characterization theorem. What do you minimize? You minimize, in this particular case I will write T integral 0 to L T and phi prime square dx. Okay. That is a quantity that we will minimize, subject to some conditions. Actually, this is not just unconstrained problem, subject to some conditions, and which are, first, that normalization condition, that is rho phi square dx is equal to 1, put that, and then we have orthogonality, that we consider several other eigen functions. So, we will need to write rho phi that we are considering times, let us say, phi I dx equal to 0, where I goes from 1 to 3 so forth up to k minus 1 only, okay, because we are asking for kth eigenvalue. We put this orthogonality up to k minus 1, and then there is orthonormality that we are ensuring with that new function, that phi. When you get that phi turns out to be phi k x. When we find the solution, that turns out to be phi k. Okay. That turns out to be phi k of x, right. So, there is one more condition we have to put, and that is our eigen thing itself. There is phi j double prime lambda j rho phi j equal to 1, j equal to 1, 2, 3, any number, infinity, right. We do not limit it. Okay. So, this whole thing is our theorem. So, this whole statement we have is our theorem. What is this theorem? It is minimum characterization, theorem for eigenvalue problems. Okay. So, if you already have with you k minus 1 eigenfunctions, because that is what we are including here, k minus 1, then you can find the kth eigenvalue and of course, the corresponding eigenfunction by solving this calculus of variations problem. Okay. This can be proved rather easily without using Euler-Lagrange equations. That takes some time, even though it is not complicated, several steps are there, simple steps, not unlike what we have already discussed to see how all lambdas are non-negative and orthogonality of eigenfunctions, similar steps. When you do that, you can prove this theorem, and it is numerically very important, because we are trying to we are able to define the eigenvalue, that is a kth eigenvalue. Okay. If you want to get the first eigenvalue, it becomes simple, because then we will not have these things. Yes, k minus 1, k equal to 1, none of them will be there. We will just have this eigenfunction relationship, and this we will be able to do. That will be useful for us in structural design, which is what we will consider in the context of buckling. Buckling is also an eigenvalue problem, because when you take a, let us say, a beam or a column as we call it, when you take that, okay, when we take a compressive load, this column will become unstable beyond a certain value of this compressive load. We all have the familiar things. When you take this column, when apply the compressive load on it, at some point it will just bend like this, okay, or it can bend like this also, or it can bend like this also, or many other ways. So, there are many buckling mode shapes, buckling mode shapes or eigenfunctions. So, mode shapes are eigenfunctions of the corresponding eigenvalue problem. In this particular of a string problem, our equation is T phi double prime plus lambda rho phi equal to 0, and similarly if I were to take a bar before we go to columns, let us take an axially, this is for a string with tension T. Okay. If I take a bar, okay, where everything deforms only axially and it has a cross section area, this is cross section area, and E is Young's modulus, and this axial deformation we denote by Ux. That also leads to this same phi. Okay. The eigenvalue problem that we write there will be E A U double prime plus lambda, the rho will be there, mass density for it also, mass per unit length, into U equal to 0. Okay. E is Young's modulus area of cross section, you get that. So, if you see the similarity between these two equations. Okay. Again, if you assume that U is a function of x and t, you can break it up into phi of x, q of t, just like we have done for the string, you can do for the bar also. So, we have one is bar and then this string and bar, you can do this. Here also you can get eigenvalues, eigenfunctions, you get Rayleigh quotient. Okay. Rayleigh quotient in this case, which we denote by R, Rayleigh quotient, following the same thing in this separation of variables and substituting into the equation and so forth. How do you get the equation to begin with? This equation, just use Hamilton's principle. You write strain energy for the bar, you know kinetic energy of the bar, how to write it, you follow Hamilton's principle, Lagrange equations, you get that, and everything is the same. You can do for the beam, you can do for the column as well. Okay. Every one of them will Rayleigh quotient, and you will get a minimum characterization theorem such as this for all of them. Okay. First of all, there are infinite eigenvalues and hence infinite eigenfunctions, and there is a this minimum value, okay, for a beam, for a bar, everything. Okay. So, Rayleigh quotient, if you were to work it out for a beam, again you can write kinetic energy, potential energy for a beam or strain energy that you need for free vibrations. If you do this, Rayleigh quotient for a beam turns out to be E I, E is Young's modulus, I second moment of area, phi double prime square dx 0 to L divided by 0 to L rho phi square dx, this for a beam. I should write it for the bar, right, because you are discussing bar, it will be similar. It is a ratio, it is a quotient 0 to L E A phi prime square dx. Instead of T you have E A. Okay. T is tension and this will be E A, will have a similar equivalent thing, then we will have rho L and we will have rho phi square dx. Okay. So, Rayleigh quotient can be written, but main thing is this is phi double prime square, phi square, it is phi prime square, phi square over there. Similarly, for a column, for a buckling load, because that is also is something that is eigenvalue problem or buckling, Rayleigh quotient for buckling, that also becomes the P critical, the critical buckling load, that if you do the same calculation you will get 0 to L, this will be E I phi double prime square dx divided by 0 to L. Here it will be rho phi prime square. Notice that for a beam it is just phi square, it is phi prime square. So, you can get the buckling equation in this form, right. So, what we need to look at this function, the constants, I mean these things do not matter for us, the value of P critical you need it, otherwise you get, okay. So, actually density will not be there, so this rho should not be there for the buckling. Again I am writing the form of the equations, but you have to work it out by writing what is the strain energy when in a column buckles and what is the strain energy, what is the kinetic energy, you follow everything, you get these equations, okay. You can get the critical values, these things will be eigenvalues for this thing, okay. So, what we will do is we will use this Rayleigh quotient concept to design the strongest column, that is a column that will not buckle, that is the buckling load will maximize. So, for that this concept of Rayleigh quotient is helpful, okay. We did it in detail for a string, but I encourage you to do it for a bar and a beam, but also for a column, okay, to see how these critical things come about, alright. So, what we will do next is to look at the, we have discussed mechanics now, we will discuss design. When I say design of a strongest column, again of strongest column, that is we maximize the buckling load, we maximize the buckling load, and that is what we will do, okay. So, the highlights of what we have discussed today is that by starting from Hamilton's principle, we can write the equation of motion for elastic systems that are vibrating under no external force, this free vibrations, okay. And then we got eigenvalue problem for those where we have eigenvalues and then eigenfunctions, that is eigen equation we got. We solve the eigen equation by assuming separation of variables, that is space, that is x variable dependence, and time we separated out like phi of x times q of t. That led us to something that is constant, okay. Some that depends only on space, some that depends only on time, they both are equal, so it will be constant, we call it minus lambda and got two equations and said that there are infinite eigenvalues and hence infinite eigenfunctions. And when we proved that eigenvalues cannot be negative, they are non-negative, and we also proved that eigenfunctions are orthogonal, they are perpendicular to one another. So, that gave us the ability to write the Rayleigh quotient and also express any function in terms of these orthogonal functions. The Rayleigh quotient is important because that will give you the value, let us say P critical, correct value even when this phi that we have is not very accurate, and that it is going to, this is going to be the minimum value no matter what you change for these things, okay. That is why you pose this minimum characterization theorem for eigenvalue problems, and that they all go under. What will be different is just the operator, that is we are taking a function, doing some operation and then finding that that is just equal to the function times a constant. That is the nature of this eigenvalue problems or Sturm-Liouville problems, okay. Next class, next lecture we will discuss the design of optimal design of a strong column or rather strongest column. Thank you.